Okay, well, in this first activity, we want to take what we've been learning about plate tectonics and apply it to our study area, the area that we'll be going to during the field trip later this year. And so what we want to do is see if we can identify in some detail where we think the plate boundaries are in the region of the Pacific Northwest. And now remember, you want to have watched the various tutorials and thought about them, discussed them with each other. We have some basic concepts that relate to plate tectonics, in particular that plates are rigid, most of the deformation will occur at their boundaries, and that they're moving with respect to each other. Since the deformation's occurring at their boundaries, that typically is going to be an area of earthquakes, but also it might be an area where we develop elevated topography or other evidence of plates colliding or otherwise interacting with each other. So we're going to focus particularly on the region of our study, and remember the field trip in May is going to extend from southernmost Washington state here all the way down to the San Francisco Bay Area. So this is essentially our study area. We'll particularly go to places like Mount St. Helens, along the Oregon coast, this area behind the volcanoes in eastern Oregon, and then we'll come down and go to the area of the Mendocino Triple Junction. So this will be our basic study area for the course to learn about many of the processes. But to do that, we need to know where the plates are and how they're interacting. And so we have several plates in the area, the North America, the Pacific, and the Juan de Fuca. And this map, which shows on-land topography and offshore bathymetry, this is just a Google Earth image, shows us essentially the area we'll be looking at. So for this study, we're going to be looking at this area in quite a bit of detail. Now, there'll be a series of activities you're going to need to do to complete this exercise. They're outlined here. We'll go over them in more detail at the end of this little introduction. But you're provided with three basic maps: a base map that has oceanic ages, and a map that shows earthquakes. And essentially what you're being asked to do here is determine where you think the plate boundary locations are in the map that you have, and then identify and name the three plates in the region. Those are the Pacific, North America, Juan de Fuca. Assign those to one of the three or any of the areas you see, and then to the degree that one can with the data you have, try to determine such things as the directions of relative motion along each plate boundary, and also potentially the type of plate boundary it represents. That is it a mid-ocean ridge, is it a subduction zone, or is it potentially a transform fault? Now, one key thing, you are going to be working with real data. This is the actual data that we have for this region. That's good in that you'll have the best data set available, but it can also be a bit frustrating at times because the Earth doesn't always provide us data where we would like to have it. And so there will be areas that are sort of unclear, and you're going to have to do your best in terms of trying to interpret what you think might be going on there. Or you maybe just will have some gaps in your interpretation that you aren't exactly sure what's happening in a particular area. That's okay. That's the way our science moves forward. We identify the things we don't know and then put our efforts to trying to work those out. Okay, so let's move on and talk a little bit about the specifics of what we're doing. We've seen this map before, which is just a digital map, or it says of the activity on the Earth, and this shows the various plate boundaries. The mid-ocean ridges are shown here in red, for example, down through the middle of the ocean, and other plate boundaries, for example, the subduction zone along western South America is shown, the subduction zone along Japan and the western Pacific, and then some of the major strike-slip faults are also just shown as connecting these structures. We're going in particular want to focus on this area here. This is our study area up in the Pacific Northwest. And on a map of this scale, although one can see that the various plate boundaries have been put in, there are some transforms, there are, so here's a transform, there's ridges. At this scale, it's really hard to see the details of what's going on. We want to zoom in and try to place our plate boundaries either as precisely as we can, or if there's a diffuse area that we may consider a plate boundary, to identify that. So, back to our study area. Remember, we're going from this whole region of the Pacific Northwest of the US, and we're going to try to utilize particular data from the offshore to help us define where the different plate boundaries are. And we'll go through first the data sets that we have to work with, and then we'll look at an example from another section of the plate boundary related to North America, and use that as a learning tool to decide how we want to place plate boundaries here. Okay, so what do we have? Well, here is your basic base map of the study area. This is going to be the map that you're going to annotate, that you're going to identify what you think the various features are. And what we have the land elevations are shown in the greens and browns. The oceans are the white down to the deep blue. The deeper the color, the deeper the water. And so we're going to have a lot of features here, and you're going to want to pay attention to them. The bathymetry, the elevations tell us a lot. You know, we see some very interesting behavior in the vicinity of the coast, where the seafloor bathymetry changes quite a bit. We have features such as this that are also quite interesting, that we're going to want to focus on and think about what those represent. Now remember, from the lectures we've had previously in the tutorials you've seen so far, this was an area that was one of the first areas that was used in terms of plate tectonics to define such processes as mid-ocean ridge spreading and our ideas about how the age of the oceans varies with distance from the ridge. And so we have in this area the data, the magnetic lineation data. We've seen this figure before. The figure on the right here is the original data set, where they've simply colored in dark the regions that are areas that have magnetic polarity, or the direction of the magnetic field is normal or like today, and those that are in white or the areas that are reversed. Using the time scale that was developed, one can assign ages to that, and we get the figure on the left here, which shows the assigned ages. Now, it's a little messy. We see the general patterns of symmetry, etc., but there's other things going on that are complicating the features that go beyond the simple spreading at the mid-ocean ridge. So, one of the things people can do, and has been done, is they've taken this data set and similar data sets for all over the world, assigned ages to each of the spots, and smoothed them out a bit to get rid of any of the local effects. And so that's one of the maps you have to work with. That's this map here. It's what I'll call the age map. And in this map, the seafloor is now colored according to its age. If we zoom out a little bit, we see that it ranges from about 0 age to something greater than 10. Each one of these intervals represents a million-year interval. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 million years. And if we go over here, we see we go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. So we can look at this, and with this we can determine where we think the youngest ocean is, and that's going to be this area in here that's along these that are less than 1 million years old. And then we're also going to have the ability even to say, you know, if this is 5 million years old and it moved away from somewhere over here, we can figure out how fast it was moving. So we have that type of data set to tell us something about the age of the oceans, the patterns of symmetry, etc. So that's one of the maps you have, and it will, in conjunction with this map that shows the bathymetry, you may be able to figure out a lot of what's going on. And then the other main data set we have to determine plate motions, plate boundaries, plate tectonics is where the earthquakes are. And so here is a map. The other big map you have is a map of the earthquake locations. And their earthquakes are shown here. The size of the circle represents the size of the earthquake. So for example, these earthquakes up here in the north are larger than these here in the middle. They're also color-coded a little bit for depth. Ones like this down here, some of these lighter colored ones, are deeper than the ones that are more the pinkish color. But all the earthquakes that show up on this map are relatively shallow in this case. Now, one of the things we see looking at the earthquake map is that there are locations where there are lots of earthquakes and there are other areas without earthquakes. That fits into our model of plate tectonics. But we also see that there are features that we maybe believe to be of relevance as a plate boundary that don't have earthquakes. Unfortunately, it doesn't go both ways. Although we think of earthquakes as delineating plate boundaries, it's not necessarily true that all plate boundaries are delineated by earthquakes. And so we're going to have to do some interpretation and interpolation to figure out what's going on. And these are some things to think about, and then we can also look at in some detail and discuss next time when we meet online. Okay, so these are the data sets that you have for the Pacific Northwest. And before we get started on it, let's look at another location and see how that has been interpreted, and you can use that to give you some insight. So we'll go look for right now at the area where we have the intersection of three plates, essentially. We have the Pacific, we have what's called the Cocos, and we have North America. And all three of these plates interact along the Mexican and Central American margin. And so we see that in this case, they've identified a series of different parts to the plate boundary. We have sections like this and this that are a mid-ocean ridge. We have sections along here that are a major transform. So this is a ridge. That is a transform. And then we also have this area along here that's been identified as the Middle American Trench. So this would be a subduction zone boundary. So in this case, all three types of our principal plate boundaries exist, and then we can look in a little more detail as how they've been selected. So if we zoom in on this area in here, we can see what that looks like. And so here is just a zoom in on that area, and we can see how the different data are used to help us understand. Now, what's not shown here are the magnetic anomalies. They show some patterns that fit this interpretation. But what we do see are a couple of things that we can use in other places. For example, we see this relative symmetry in the seafloor away from the ridge here. So we have the ridge coming down, and we can see in the fabric of the seafloor both here and over here this sort of pattern of symmetry. And if you had age information, it would show that also. So it's easy to interpret this as a ridge. One of the things we also do see here, though, which is really important, is that ridges in general do not have a lot of earthquake activity on them. We tend to have the earthquake activity along the transform faults between the ridges, not on the ridges themselves. Ridges have earthquakes, but they tend to be smaller earthquakes and maybe wouldn't show up in this sort of a data set. And so in your case, you may see that sections of the ridges do not have earthquakes. That does not mean they're not an active plate boundary. Whereas the transform faults tend to be the areas that have lots of earthquakes on them. Another thing we can see is how they've defined the position of the subduction zone trench. And that also is tricky in that the plate boundary as drawn here is not exactly where the earthquakes are. And in fact, there are some sections along here for which there are no real major earthquakes. There are some gaps in the earthquake activity, and yet this is still interpreted to be a subduction zone. The key thing, though, is the subduction zone is inferred to be located where there's a substantial change in the seafloor morphology or bathymetry. You can see this boundary here is going along what we would call the break and slope between the shallow oceanic part of the system and the deeper part. And in some cases it's deep enough here that it's called a trench. In some cases that may not be what we see. So in this case, the criteria of areas that have earthquakes are typically plate boundaries, and also the interaction of the plates moving apart, and we get the shallow bathymetry in the vicinity of the mid-ocean ridge because of the hot material that's below it. We get the change in bathymetry where we have one plate, in this case, going down underneath Mexico. So in this case, the Cocos plate is subducting beneath Mexico. We can use all of those informations to try to identify what's going on in our region. So back to your assignment, or what you need to do is for this region, and you have the more detailed maps of it that you will annotate. So in particular, you will use this base map and annotate it. You will identify where perhaps you think there are boundaries. You may draw on this in some way or another, label them. In the end, you will turn this in by either scanning or taking a photo of it and submitting it. But the idea would be that you can use the combination of bathymetry, age from magnetic lineations, seismicity, and other features to say something about where you think the plate boundaries are here. What exactly do you need to turn in? Okay, so let's get to the deliverables for this. So for the first part of it, you will basically turn in that map, annotated, written on, drawn on, where you've labeled the different plate boundaries and any of the information you have for that. So essentially what you will want to do is complete this part of the exercise, which is to sketch in the plate boundaries, identify and name the three major plate boundaries, and best estimates of directions of relative motion and the type of plate boundary it represents. Then to bring it all together, you'll be asked to then supplement your map with a short report, about a 1-page, that's about 500 to 700 words, depending on spacing, etc., that details the evidence and the approach you use to locate the plate boundaries. It should be written in a very direct style. That is, this doesn't need to be flourishy, it just needs to be the points. I would recommend that you systematically go through each of the plate boundaries. You may, for example, label them on the map, plate boundary A, plate boundary B, plate boundary C, and describe how you determine the type of plate boundary it is, why you put the plate boundary where you did, and what you can say about its behavior. So this would be essentially, you might say, for the mid-ocean ridge in a particular spot, you selected that based on its bathymetry, that was such and such, and that it had a particular age, behavior, or earthquakes were occurring in a particular place, and so on. You may also have gaps in your plate boundaries. That's okay. As I said before, plate boundaries, this in particular, the Pacific Northwest boundary, what we call Cascadia, is problematic. There are places that it's very unclear exactly how it's going on, and it's still an area that many of us are actively working on to try to understand better. So this 1-page report will also be turned in with the map that has been annotated. So that's where we're going to go. If you have problems with this, let us know. We'll be happy to help, and it's something also we can discuss during the class meeting time online. So good luck with this and have some fun with it.